The broadcast is now starting. All attendees are in listen-only mode.
Hello everyone, welcome back. I guess we'll give the rest a couple minutes to get here, but we'll have a slightly shorter lecture today, followed by Mr. Dubik. He should be coming on about halfway through, and we'll be printing out your design. So I guess if you haven't submitted your designs yet, I'll go to this slide. It has some information. You can ignore the code combat thing, but make sure that you've done these steps. Saving it with your first name. I think if you leave out your grade level, that should be fine. Make sure it's public. Make sure it's on Edmodo. If you haven't done that yet, now would be a good time to finish that up. Hey Gabe, we're just going to wait 1 or 2 more minutes. That is to see if anyone else is going to show up. Hope you guys had a nice weekend. Mine was pretty good. All right, so we're going to go ahead and get started now. So materials engineering. So as you guys might remember, I was a chemical engineer, which has some similarities to materials engineering, but is different in certain ways, and I will be able to point those ways out. Materials engineering is also very similar or very related to mechanical engineering as well. In fact, probably if you looked at what mechanical engineering and chemical engineering has in common, then that's pretty much what materials engineering is. It's the blend of both worlds, because in understanding materials, you have to understand both the mechanical properties and the chemical properties to understand how to manipulate them. That's not true across the board, but very generally. So let's get started. There's some pretty cool new materials that we have created today. The first example is liquid metal, which we're going to watch a video about from Modern Marvels. So it's twice as strong as titanium, very resistant to scratches, very resistant to scratches. That's a double bullet point. That's probably a mistake. So, as you can imagine, strong things are really useful, especially in small things like cell phones, where we're getting bigger and bigger screens. So to keep them light and thin, we want to keep the weight down, but the strength up. So cell phone manufacturers are interested. Let's go ahead and watch the video to find out more about it. Oh, also, I'm going to post this link just in case let me know if it's if you're not getting are able to see the video very well. And I'll give you the link there so you can copy it and watch it too on your own, or as we're doing this. If not doing well, I'm starting at 1 minute.
From copper and iron to steel and aluminum, our progress has been marked by newly applied metals that are stronger and lighter, though fundamentally similar to the metals that have come previously. But the metal of the future might just be a new alloy that behaves in ways we've never seen metals behave before. The true future metals may not be the so-called new metals like titanium, as much as new structures, taking it all down to the molecular level, turning crystalline solids like titanium, iron, and aluminum alloys into glasses by melting them at extremely high temperatures, then rapidly cooling them. A company in California has already done it with a superalloy called liquid metal, made of steel, aluminum, and titanium. Conventional metals crystallize when they solidify, they form crystals. Liquid metal is basically a frozen liquid. We call that a glass. Like a solid, the molecules in a metallic glass do not move, but like a liquid, they are not aligned in a uniform pattern. This molecular condition makes them very strong. Further, they have fewer structural defects because they are often fused from a powder, providing uniform consistency. This process allows them to be efficiently molded, much like a plastic, rather than forged. Simultaneously, drop a ball bearing on a stainless steel plate, titanium plate, and a liquid metal plate, and you see just how much stronger, harder, and elastic the metallic glass is. Its strength, for example, then, is typically 2 to 3 times stronger than the same material in the crystalline state. As scientists continue to create new metals with unusual and original properties, other scientists are busy developing applications for those metals. Around we go, from discovery to invention, as we have for thousands of years. Ever since that first person pulled a lump of molten copper out of a fire and forged it into shape, transforming a collection of people into a striving civilization. This molecular condition...
All right. I'll pause this and come back to that later. But yeah, so these new metals have a lot of promising features. Let's see something else, some movements. Yeah, another cool new material, graphene. It's the strongest material ever measured, 100 times stronger than steel by this, for the equivalent amount of it. It's stiff, thin, and another possibly next big thing. But again, uses are limited so far. So let's see what it's about. Here's the link. This one we're going to start from the beginning.
Graphene. Everybody's talking about it. When hearing some of its basic properties, you might have wondered if people were confusing it with some kind of substance only found in comic books. It's 1 atom thick, conducts electricity better than silver,
Say it's really hard to understand. Is that because of this, playing it through the computer? If I turn the volume up, would that help? Yeah, okay. I'll go all the way up. I'll start back from the beginning, too. I know you speak
graphene. Everybody's talking about it. When hearing some of its basic properties, you might have wondered if people were confusing it with some kind of substance only found in comic books. It's 1 atom thick, conducts electricity better than silver, conducts heat better than diamond, and it's stronger than steel. It would take the focused force of an elephant balancing on a pencil point to pierce through a piece of graphene as thick as plastic wrap. And yet, graphite is made of the same stuff. And yeah, that crumbly stuff used to make your pencil is
a lot less impressive. So what's up? Graphene is made of carbon, and carbon has only two naturally occurring crystalline structures. Graphite, which is just stacks and stacks of graphene piled on top of each other, and diamond, which is a network of carbon atoms arranged into tetrahedrons, one after the other. For being composed of entirely the same element, those two things don't seem to have a lot in common. Diamond is clear, graphite is black. Diamond is a nearly perfect electrical insulator, while graphite is both a great conductor of heat and electricity. The differences between these substances all come down to the arrangement of their atoms. Carbon has 4 outer electrons. In diamond, all 4 of those electrons bond to carbon atoms around it, forming those tetrahedrons. This makes for an extremely rigid and strong crystal. An insulator because there are no leftover electrons to carry a current, and it's clear because light can't easily excite electrons that are tied up in such stable bonds, which is where they'd otherwise be absorbed. Graphite, on the other hand, is a crystalline form of carbon in which each atom is only bonded to 3 other carbon atoms. Those atoms form a 2-dimensional sheet of hexagons in which each atom has 1 unpaired electron left over. And those electrons will go flying across the matrix of atoms if you apply an electric current, allowing it to readily conduct electricity. They also gobble up any photons coming their way, which is why graphite is black. But while graphite is a great conductor, its natural form consists of layers of those sheets. So if a current is applied to it, those free electrons have lots of different directions they can go in, taking tangents up and down and left and right and so on. But if you strip away just a single layer, forming graphene, then you have what amounts to an electron superhighway, a flat matrix of carbon atoms for that current to fly across. And those sheets of carbon are pretty easy to separate because they're not molecularly bonded to each other. That's why graphite is so soft. Instead, they're held together by van der Waals bonds, kind of a weak electrostatic bond that's the same force that makes sticky tape sticky. And in fact, graphene was only discovered in 2004 when 2 physicists at the University of Manchester, Andrei Geim and Konstantin Novoselov, decided to use sticky tape to peel off thinner and thinner layers from the slab of graphite. Eventually, they got a layer just 1 atom thick. So that's what it is. But what is it good for? Because of its terrific conductive properties, scientists are excited by the possibility of using graphene as a replacement for silicon in microchips. Not only can electrons move faster across graphene, they're also subjected to less noise. That means the electron can move from one side of the sheet to the other in a straight line without detouring around a whole lot of atomic potholes. Scientists think that graphene transistors could operate at frequencies of up to 1,000 gigahertz. That's 10 times the maximum of silicon. Another proposed use for graphene is in touchscreens. The topmost layer of a touchscreen has to be an excellent conductor of electricity so the device can sense your fingertip. The material we use now is indium tin oxide, but it's both rare and brittle. Even ground into powder, graphene retains many of its extraordinary properties, so it could replace graphite or other forms of carbon in anything from car tires to AA batteries to make them stronger or more conductive. The biggest problem with graphene, though, is how hard it is to make. I mean, peeling off a tiny sheet at a time with sticky tape isn't really scalable. We can grow graphene sheets by heating up a sheet of hydrocarbons like methane until the hydrogen separates, leaving only the carbon behind. But the graphene we get from this is mostly low quality. Basically, it's hard to create a 1-atom thick sheet of anything. And it's also really hard to get a completely pure sample of anything. And here, we're trying to do both. But then again, the silicon industry faced the same purity problem 50 years ago, and we eventually solved that problem with time and some money. So with some more time and some more money, I'm sure we'll do the same thing for graphene. Thanks for watching this SciShow Dose. If you'd like to help us keep exploring...
All right, so he covered a lot of things really quickly there. So was there anything that you guys caught that you want to hear again or help me to explain in particular? I know he covered a lot of things really fast. Let me see if I can see some, go back to some key slides. So obviously the color is different. He was talking about how different, even though they're the same material, it's really how the atoms are bonded and whether the electrons are stuck with the atoms or if they have free electrons as to whether or not they can conduct electricity or not. If they have free electrons, the electrons can fly around and just kind of hop from one atom to another. And so that makes something easy for electricity to flow through it, because electricity is just moving electrons really through something very quickly, whereas diamond's electrons don't want to move away from their nearest atom. So they stay there. let's see. Yeah, covered a couple of other things. Yep, that's the bonding thing. So here he's talking about covalent bonds, and he mentioned van der Waals forces too. So this one sheet here is graphene. If you stack a ton of these sheets on top of each other, you get graphite. And so what happens is when you use your pencil, which is made out of graphite, when you write on a piece of paper, these graphene sheets, just not necessarily one atom at a time. For you to see it, it's probably many atoms thick. But you're just rubbing off sheets of graphene at a time onto the paper. The graphene's not actually breaking, but the layers are coming apart. So you might have, just for example, his numbers aren't real, but if you had 8 layers on top of each other and you drew a line, you might have like layers just like coming off one in front of another, so that your line is just a bunch of different layers that kind of all rubbed off. And maybe the layers, if a layer is like pointed down into the page rather than parallel with the page when you write, it might flake off instead of actually sticking to the page, and that's because and that's why you get, when you write, you get those little bits of pencil dust all over the place. And even if you were to rub your hand over it, you're making those, you're rubbing more, over what you've written. You're making even more layers come off, which that's okay. So that, I was going to bring that back to the van der Waals forces. So covalent bonds are fairly strong molecular forces that hold atoms together. Now, van der Waals forces are much weaker forces that also hold atoms together, but just compared to the covalent bonds, it's like the strength of an infant compared to the strength of a muscle lifter or something. They can lift many, many times as much. So really, compared to covalent bonds, van der Waals forces don't really have much effect. So that's why they just come apart so quickly. Let's see if there's anything else. Yep, there's van der Waals, the people that made it. And then notice, here's some other properties that are not so easy to explain. But let's see. Yeah, so let's keep on going. So these new materials, it's one thing to discover or invent something, but manufacturing is a different story. And that's where materials engineering, materials engineers tend to focus on either, not necessarily, but a lot of materials engineers focus on the invention of a new material, or the small improvement of a material property in a material, or kind of are on the cutting edge. But then there's another section of materials engineers who might work on a process alongside of chemical engineers and mechanical engineers at a plant, who where they're focusing on understanding the material so that they can tweak it to make it a little better. But it's this idea of the process, discovering to manufacturing. That's a really big difference, and we're going to get back to that later. But he mentioned that we discovered silicon 100 years before we understood how to turn that into a chip, a silicon chip that we could use to power computers. So it's similarly likely, even though maybe it might not take 100 years, or it might take more than 100 years. With the pace of invention speeding up, it could be faster, but these things take a long time, on some scale at least. So, so basically one of the big things is the adaptation of the marketplace. You might wonder why you don't see this stuff in the stores. And there's usually two reasons. A, you have to be able to make it. B, it has to be better or cheaper than products. And it actually has to be much better or much cheaper for someone to have the incentive to take that risk to produce it in the first place. If it's not really obvious that it's going to be better, then someone might not take that risk until the economics are more in their favor. You pointed out silicon and also aluminum was discovered in 1985, but it was actually a very, very rare metal. There was a monument made out of it until they realized it was like this. A very prized monument was made out of aluminum, and until 30 years later they realized, oh, this is a really cheap metal. But it was expensive then. It was used in jewelry, in the nicest jewelry because it was so rare. And now they learned how to mass produce it in the 1880s. Aluminum made it airplanes made aluminum super popular because they really like the lightness, but the strength, like the lightness of the aluminum for its strength. You can imagine why that would be useful in an airplane, to be light, but still strong. And so that really made the manufacturer, gave the manufacturing plants incentive and the monetary incentive to actually produce a lot of aluminum. And then once it was being produced on the high scale, the cost came down as a lot of aluminum was produced. And then once the cost came down, then we started seeing it used in common household appliances. You probably have aluminum, just thin sheets of aluminum in your kitchen right now in aluminum foil, which we call tin foil, but it's actually aluminum foil. And in hundreds of other materials, often composite materials, which we're just about to get into. So what is materials science? Let's be specific about this. It's the study of solid matter, and not necessarily just solid matter. It has to do with understanding the liquid and gas behaviors, but it tends to come back to solid. How does it act as a solid? And usually it's manipulation as a liquid. Materials scientists investigate the relationship between the atomic or molecular structure or both of a material and its micro and macroscopic properties. Microscopic properties being things that properties that happen at the atomic level and the invisible level. Then macroscopic properties being like how much weight can this hold if you put a lot of pressure on it. Whereas microscopic, how do these individual atoms behave and that sort of thing. So then also they try to examine and understand what influences the properties of the material so that the right material can be selected for a particular application. People, in materials scientists, they don't go into I think I'll look at that in a little bit, Gabe. I'm going to keep going for now. We've got a lot to get through. So, where was I? Understanding the properties of the material to be selected. So that's, material scientists who don't go into research and academia trying to find new materials, they might go into, they might be hired by a company, even though they probably have a PhD in material science or something. They probably, they could still get a job either consulting or working for a company who needs to understand. They have an application. They don't know how to make something, or they want to make something new, and they need to understand what material to select. One example of this is those all the watches that are coming out, the smart watches, the Fitbits and that sort of thing. Well, they have to select a material that Fitbit has a little chip in it that can come in and out that is the has all the components, but then there's that band that that holds it in. So the band has to be strong and not break very easily. So that's one way that had to be integrated together. Also, even some more artistic things. There's a kind of a glove, I guess, that someone can play music with by moving their fingers around, and there's wires in there, but it's all based on the movement in your hand. I just remember seeing a documentary on that one time. But okay, so back to material science and materials themselves. So typically there's 4 categories of materials. Not everything falls into one of these categories, but most things do. So there's ceramics, metals, polymers, and composites. Now, ceramics are you definitely have ceramics in your house. You almost if you're not a college student who doesn't have any cooking supplies, which I know you guys aren't, you probably have some sort of cooking ware or pottery mugs, pottery bases, some sort of container made out of usually it's created from clay or some other sorts of powders that were heated up. Fine china, or all the way from fine china to pottery to like the ceramics. Corningware is this branded example, but all of the casserole dishes, those are very common ceramics. They're not just used in the kitchen, but those are probably the most popular ones. In general, ceramics are brittle, hard, strong in compression, but not at tension. So you wouldn't want to make a chain to hoist something up with ceramic chain links, because they're brittle. So if they bump against each other too hard, they're going to crack. Also, they're not strong. They're strong in compression. So you can sit some heavy things on top of them, but you can't stretch them out. So, another thing is they're typically really good at withstanding corrosive environments at high temperatures, which you might not think of your kitchen as a corrosive environment. But some foods, in fact, if you use copper pots, you can't put acidic things in them, because that acidity will react with the copper and actually poison your food. So you have to be careful with some metal pots, but ceramics are fairly, they don't really react very much to many things at all. Almost nothing reacts to ceramic. And they also withstand high temperatures. You obviously would think to stick a casserole dish in the oven. That's what it's made for. So that's why you do that. Let's see. So ceramics, silica, alumina, Corningware, porcelain. Those are some examples that were listed on the side here. Silica sand. You don't necessarily think of sand as a ceramic, even though it is, and that's only the silica, the pure sand, not necessarily the sand at the beach. That's a slightly different material that we could get into it next time, maybe. I actually spent a third of a semester learning 3 or 4 weeks just learning about the properties of nacre, which is N-A-C-R-E, which is, so you can look that up if you like. It's fairly interesting, but also probably pretty some heavy reading. But that's what you might think of as sand, which is the stuff that gets broken down from the shells that of seashells and the shells of living creatures back from the ocean, that sort of thing. So next we've got metals. I think you guys have a good idea of what metal is, but some properties. They have good electrical and thermal conductivity. If you think about it, if it's cold outside and you stick your hand on some metal, your hand's going to get cold really quickly. If you stick a metal pan on the oven, you stick your hand on it, it's going to get hot really quickly. So that means it's got high thermal conductivity. Also, you think of copper wires. In general, most metals are good at conducting electricity. Copper wires are some of the best. So some unique properties. Metals are metallically bonded. That it's a fairly unique bond in that it's just kind of like we were talking about the van der Waals forces that hold atoms near each other, and the covalent bonds that actually are bond things together. Metallic bonds are another type of bond that really just metals have, and the electrons are all shared in like an electron cloud around all the protons, which are stuck together. So the electron, that's what makes them very electrically conductive. Then they're also malleable and ductile because they share electrons, and they're surrounded by an electron cloud. When you move when you dent a metal, the electron cloud just kind of forms in around it, and it's still all of the protons are still surrounded by other protons. In general, it's fairly resistant to malleable is the opposite of brittle, which we said ceramics were generally brittle, hard, and strong in compression. Well, metals are malleable, ductile, and strong in tension, and can also be strong in compression, but are much more, generally speaking, strong in tension. That's why you see the bridges that hang, the suspension bridges, with the long pole, the wires, holding up the bridge from a tall point. Well, they build those poles out of something like concrete, or maybe possibly metal as well, but something very strong in compression. And then those wires, which are in tension, the bridge is pulling the wires apart. The wires are in tension, so the metals are good at that. Common metals: iron, copper, gold, silver, tin. Some alloys. Alloys are just if you take some of the elements and mix them together, you get steel, nitinol. I've never heard of that one. That's steel, I believe, is iron and tin. I should know this. Nickel. Okay, we'll look it up in a sec. All right, then we have polymers, if you break this word down, you've got poly and mer. Take off the S. So MER is, I think it's Greek, it could be Latin, but it means unit. Poly means many unit. A unimer is one unit. A bimer is 2 units. Polymers is just many units. So a polymer is, starts off with a single chemical compound, but it reacts with itself in at least 2 places. A monomer is not a unimer. A monomer, that you might have heard of a monomer before. And so one monomer has to have at least 2 active sites on it, and that means if it has 2 active sites, think of your hands as being active sites, and a bunch of people you're in a crowd, and you all start linking hands. Well, you've got 2 hands, so if everyone only had 1 hand, everyone could link up, but they wouldn't have another hand to continue linking. So the biggest chain anyone could make was a chain of 2. But with 2 hands, you can start linking up, tons and tons of people. So imagine if everyone started holding each other's hand, and until everyone's holding someone's hand, then in a big room, then you've got something like a polymer. That's very similar. Someone might think, what are you doing? Well, if you go in your chemistry class, if you have a particularly active chemistry instructor, they might have you do this exercise so you can really imagine what a polymer is doing. Then someone else might think that, and then you'd have to explain to them what a polymer is. So there you go, Gabe. By controlling what material scientists do is by understanding how polymers are created, they can create different types of polymers. Imagine if you had everyone line up and hold hands, but no lines ever cross. So you have a lot of long strands, then you might get something like nylon, where it's really, really strong, tight fiber that's really amazing at tension. Nylons are really strong material that can really hold a lot of strength, in tensile strength, for its weight. Kind of like it's what makes nylon makes rope. Rope is very commonly bought, obviously. So that's the material selected because it's one of the best. Some other properties: all plastics are polymers, but just imagine all of the different types of plastic. In your kitchen, you've got plastic wrap. You've got your phone has plastic on it. Your pens are have plastic in them. You just look around the room and you see so many. You can see so many things with plastic in them, and that didn't even exist much more than 100 years ago. So let's go back to the properties. They can form glassy and semi-structural structures. They're almost never crystalline because in the way they react, they just they grab onto two things quickly. But if you imagine a pot of liquid polymer all linking up all at once, it's really going to be hard to make something very crystal because there's just so many active sites where they can just grab on. So they're often very intertwined and very not structured. Whereas you might diamond is super structured. All of the atoms are perfectly aligned and there's very few flaws. But it's actually the flaws, the not linking parts that give these plastics, polymers, their material. And also things like wool, hair, those are also polymers because they have the repeating elements. They don't always have to be the same repeating elements, but they tend to have some amount of repetition throughout the structure. I can't remember what shellac is. I think it's a paint maybe. Wool is a type of polymer. PVC pipes, plastics also tend to be fairly non-reactive. They often react with sunlight, but not necessarily. And so pipes are a big one for plastic because where metals might erode or corrode because metals can be, just in general, metals are more corrosive to small bits of acidity. The pipes in PVC, they're really good for transporting water and that sort of thing. We also use metal pipes, but you see PVC pipes and metal pipes used for different things. So, and composite materials, I see Mr. Dubik's here, so I'm going to go pretty quickly through this last bit. But composite materials just combines two things. Cement, we talked about this earlier when we were talking about the Colosseum. That's a composite. They take a bunch of rocks, gravel and sand and water. So you take a lot of different size pieces and different materials, mix them together, and they form something with some properties typically that are a blend of the materials that you use. Not always, but very commonly a blend of materials. Gravel is really strong. Sand kind of adds some, fills in the space, and Portland cement really bonds things in the water, kind of links everything together. And I'm not sure if that was the best example, but if you think about how then you have that concrete, but if you add in like the big rocks for structural support, that's one thing. But then you can add in steel, rebar, and that you created a composite with the rebar, that metal running through material, so that maybe whereas concrete, which we've mentioned before, was really, really good in compression, well, if you add that rebar in, then you can make concrete that's not only good in compression, but also pretty resistant in under tension as well, because metal has really good tensile resistance, and metal is more flexible, so you can help. It can help support the concrete when it's bent and that sort of thing. So it makes it less brittle. So that's really commonly used in building. So that's one example of how composites can exhibit the characteristics of the different materials included, so the properties are very tailored for the application. Let's see. Common composites: wood is cellulose, and lignin glue. Also, wood tends to have different properties on the outside and the inside. Tires have fiber and rubber. The rubber holds the air inside, while the fibers withstand the stress of the car, that sort of thing. Mr. Dubik, how are we doing? Should we go ahead and get started?
Yeah, we're running out of time here because we have to, let me see, am I muted here? Or you can hear me, can't you, Mr. Cato?
I can hear you.
Great. All right, guys, what I want to show you, if you'll give me the screen, we'll go ahead and pop this over here for real quick. All right, show my screen. We're going to pull this up right now. All right, this is what, right there is looking at the 3D printer and a shape I printed earlier today. It's a duck checker. If everybody can load, just so we know, Kevin, Jaden, Gabe, have you put your prints on Edmodo? Do you have the links of your 3D prints?
2 yes, 3
There
yes.
has to be checkers, whatever you want to print. What did you want to print? And did you put them up there? I'm looking over here to see. Yes, yes. My Skull and iPod case.
Yep.
Jaden has one. What about Kevin? Do you have yours up there? Okay, great. He's already put it up. Even better. Well, Kevin, that's okay. Go on Tinkercad. You don't have to do it tonight, but get it to us, and we'll print it for you, and we'll mail it to you. All right. What's going to happen is I'm going to get the link. I'm going to put it on there. We have someone that, I forgot, the high school kids come on from 8 to 9. Then I will put up, if everybody will give me your, let's see the best way to do this. I'll invite you all to another webinar, a one-time webinar tonight, and we can print some more. And then that way you can watch what's getting printed, I think is the way to go on this. Okay, I got one person who says, yay, that idea. I would love to print. All right. Well, then, Gabe, we'll get you set up there, okay? And for the other people, if tonight won't do it, that's fine. We'll figure out another schedule. Another way to do this might be even easier. I'm trying to think if we should use your email. I still like the webinar idea. How hard is it for you guys to get to the mail that you use when you register for webinars? Not very. Okay, great. All right, so I'm going to put a webinar out there. Let me do this right now. Hang on a second. And in fact, while I get everything prepped for you, let's go ahead and show you one thing here that shows a lot with composites. And it's actually a pretty interesting video. It's by Corning. It's going to talk about willow glass. While that's going on, I'm going to set up another webinar that you all will be able to join. And I'm going to send you the invite while we're here. And also, I will get then, I think, who sent me the link already here? I will send, see, Jaden already gave me something to print. So I'll do Jaden's first, just out of doing it that way. All right? And then the webinar is going to start right at 9 o'clock, this next webinar. Gabe and Jaden, tell me where you all are from. We might do the person that's closer to the East Coast earlier. Who's the earliest? All right, Gabe's in North Carolina. Jaden's in North Carolina. Okay, we got everybody in North Carolina. Well, we'll start printing them, and might be a little bit late, but you can watch it, okay? Yeah, I know right where you are. I'm in Charlotte. I'm in Asheville. I lived in Waxhaw for years in Weddington, and I go to Asheville quite a bit, so I know both where you guys are from. All right? So, with that in mind, I'm going to go ahead and put this video running just so you can enjoy that while I get everything set up for you, okay? So let's do this.
Pop quiz. If you were able to look back on the present from deep in the future, what age would you say we're living in?
Mr. Cato,
Yes.
can you do that so I can set everything up and get everybody hooked up here? If I have you make you the presenter again?
Yep.
So I'm going to change presenters. I'm going to make you the presenter. Okay. And that way I can get this done.
Okay. Let's see.
Do you have the screen?
Obvious. Can I say more than one age? Yeah, I think it is a trick question. I mean, I want to say information age, but it seems too obvious. Can I say more than one age? Yeah, I think it is safe to say that we are living in more than one age. From the beginning of humanity, we've seen prevailing technologies marked with milestones, the Stone Age, the Bronze Age, the Iron Age, all occurring many thousands of years ago. Man's mastery of these materials has defined us, but by that metric, the last couple of hundred years have seen a flurry of ages. The steam age, the industrial age, the atomic age, the television age, the space age, to name but a few. But those are not the answers I was looking for. Is that a clue? Yes, it is. I think that this age could be classified as the Glass Age. That's not what I was thinking. I know. So how are we in the Glass Age? Well, let me put it to you this way. Can you imagine a world without glass? I don't want a cheeky answer. I want you to really think about it. Okay, no. I can't imagine the world without glass. Exactly. Glass is really quite extraordinary. Without it, many of our major accomplishments would never have happened. Glass has a deep and complex history, and as a material, it has properties and characteristics that we are only just beginning to understand. We look right through it and think of it one-dimensionally. Most of us think of glass as a fragile, brittle thing that, if not handled correctly, will break in a spectacular fashion. So you're going to break that to make a point? Indeed. Can I help? Yes, you can. And it's true. Our everyday common variety of glass is brittle, but it doesn't have to be that way. Glass has already altered our lives and is behaving in ways that is totally unexpected. Got it. Let's start with a history of glass. I think I can handle that. Glass as we know it is most commonly made of silica, the primary ingredient of beach sand. Mix silica with a couple of other key ingredients, heat it all up till it melts, and bang, you got glass. Humans have been making glass since ancient times, starting with beads, vessels, and ceremonial accoutrements. Glass-making techniques spread out from Mesopotamia, culture to culture, changing in incremental ways for much of the last 4,500 years or so. The Romans even had glass windows on their important buildings as early as the 1st century A.D. Glass blowing was discovered around that time, and soon inexpensive and ubiquitous glass became one of the hallmarks of the Roman Empire. But no period has seen such growth in the development of glass technologies as in the last 150 years. We've been able to unlock the secrets of glass in ways that would have seemed like magic to our forebears. Nice. Thanks. So, tell me what's so special about the last 150 years? Well, several things. In that period, technology evolved at an exponential rate. With that came tools and processes that enabled advancement across all material sciences. The leader in glass material science was, and still is, an upstate New York glass company that started out in the mid-1800s, Corning Incorporated. One of their first products was a toughened glass lens for railroad signal lanterns that offered 2 radical improvements over any other lens of that time. It could be produced in a consistent color, and more importantly, it didn't break when rain hit the hot glass. This helped save lives by bringing down the number of train wrecks, but it also set a course for 160 years of innovation in glass. Of course, everybody knows about Corningware and Pyrex products too. Those innovations came from Corning during the early part of the last century.
You know, I have tons of this in my kitchen.
But Corning no longer makes kitchenware. They've innovated way beyond that. Let's take a look. We'll start with this.
Optical fiber.
Right, optical fiber. This does 2 things, both astonishing. The first one is this.
That right there is pure glass. A glass strand inside the cable, tightly wound around a pencil and yet not breaking. When you stop and think about it, that is a mind bender. Okay, what's the second thing?
Well, it's the way the light moves through the glass. When the glass is bent this way, you'd expect light to leak out and get weaker and corrupt the data that it carries. But that's not happening. Nearly all the light entering this optical fiber is coming out the other end.
So it has a low attenuation?
Yeah, exactly. Very low. In the late 1960s, Corning figured out how to limit the attenuation or loss of light as it travels through fiber, even when that fiber is bent.
Nice.
This discovery led to the practical use of fiber as a medium for voice and data communications over great distances, ushering in an era of low-cost, high-bandwidth communications and ultimately the Internet as we know it.
Wow. So just how much data can these optical fibers carry?
This video playing back right here is sucking in data at around 20 gigabits per second.
It's a lot of data.
Yeah, this is ultra-high definition raw video, but even in this case, the optical fiber is not anywhere near capacity. The bottlenecks are here and here, not here. The practical limit of data transport over optical fiber keeps increasing. Using today's technology, it's possible to transport more than 1 million gigabits per second, about a petabit. That'd be like downloading 17,000 high-definition movies from Netflix in a single second.
That's amazing. Okay, tell me about this stuff.
Well, obviously it's an optical fiber as well, but instead of sending light through one end and out the other, it emits light throughout its entire length.
Cool. What's it good for?
I have no idea. Okay, so I was able to seriously bend a strand of glass. Didn't break. But what do you think's going to happen when I try to bend a pane of glass? Rhetorical question. Check this out.
That doesn't look like it went very well.
Well, that was soda lime glass, the kind of normal stuff we see around us every day. But watch what happens next. This is glass too. It's called willow glass, also made by Corning. And it's flexible.
No way. I cannot believe that is glass.
Well, it is. There's no trickery here. This is glass, but it's as flexible as paper.
So what kind of applications does that have?
Well, that's where it gets really cool. Check this out.
All right. It's looks like a piece of stainless steel. And what is this? Willow glass bonded to one side as a scratch-resistant coating?
Yep.
Okay, but tell me this. How is the willow glass anywhere near as durable as stainless?
Well, that's a good question. Watch this.
That is amazing. I cannot believe that the blade did not shatter the glass.
It didn't. And that's just half the story.
All right, so what are we doing?
Give me that. Okay. Take this.
This is heavy, man. What do you want me to do with it?
I want you to drop that right on that piece of stainless steel with the willow glass on it.
Seriously.
Let's see what happens.
Here we go. 3, 2, 1. No way!
It dented melted it, but it didn't break the glass.
That is insane.
And you can attach this to just about any solid surface.
Bendy, flexible, durable glass. Impressive. And characteristics you wouldn't normally associate with glass, right?
Right. I like this new glass anyway.
How are we doing, Mr. Dubik?
Yeah, I'm looking at the Kerbal spaceship, and unfortunately, it's 45 by 45, which isn't a problem, but it's 130, and I'm not sure my build area is that high. So I'm looking at 65, 6.5 centimeters. Let me find out what my build area is on this. I think we're going to have to go at 65 centimeters there. It's just because of how much height we can do on this. Let me do it real quick. Well, print area, Polar 3D. Now, 1 second, guys. I'm trying to figure this out. Yeah, I can only go. Let me go back up your design. I can't go that high, or I'm getting right on the edge of how high I can go. Let me go.
Jaden just asked if you could make it smaller.
Yeah, I'm going to.
Okay.
I can tell you almost. What's let me see here. 6 times 2.5 centimeters. 150. Yeah, I'm going to make it. I'm going to go put it back up at 150. Here's what I'm going to do. Hang on 1 second, guys. Oh, that was. Bear with me. Sorry. Okay, now I'm going to take the whole thing. Move it down. Oops. Hang on there. I'm trying to move that down a little bit so it's on the bottom of that. Oh, that's too much. Can I pull it up? Oh, there we go. There we go. I'm going to scale the thing down. Sorry here, hang on a second. When dealing with these big sizes in Tinkercad, it's kind of a pain. Hang on. I'm sorry, guys. If you want to talk a little bit about that more with them, that's great.
Yeah, sure. Let me go back to the slides here. That was good because we didn't actually get the glass. They talked about a lot of the future of glass, where we are today in glass, and even some of the past things. They left out stainless steel. I mean, not stainless steel. Glass. Now I can't even think of the word. In churches, stained glass.
Stained glass.
Thank you. Stained glass is huge in art, especially. This vase here, with all the little different glass flowers embedded in it, that was, I believe that technique was invented in Murano, Italy. Murano pioneered a lot of glass making, especially with the colors and the strength for being so thin and delicate and lightweight. They really created. They were the pioneers of glass in the I believe yes. After the Romans took it and spread it through Italy, they kind of mastered the art of glass blowing.
Mr. Cato?
Yep.
Hey, quick interruption. Did everybody get registered for the webinar at 9:05?
Good question, guys. Jaden says yes. Gabe, Kevin. Let's see, Kevin, I guess you said you didn't have anything.
Well, Kevin, if you want to work on something for the next hour, we can at least get it going so that we get something out of it, buddy. Because it's getting close to 8 o'clock. We got to hand it over to the other high school. All right, I have modified your print. I'm going to load it up so it's all set for you to go. All right, and that print will take a little while, so I may even just start it up a little bit for you.
Gabe says he didn't get the email. Gabe, can you give us an email address that works?
No, it's not an email. It was a message on the chat bar inside the webinar.
Oh, on the chat bar inside the webinar, Gabe. Did you check there?
It was to everybody.
He says he got it.
Great. Let me see if I can get a polar cloud right now. Oh, what the heck? Let's see. All right, let's try it now. Okay, we got a problem, and it's not you guys. It's their polar cloud is down. So it may not even happen with their software. If you give me the screen, I'll even show you the message. Well, it's 8 o'clock. We got a next one. Come on at 9:05. Right now, they're having a problem. I'm sure they'll get it working. I would think they would. If not, I'll still be on. But right now, I'm going to the software. It's all based on the cloud. And honestly, look, I can go there. Let me see if I can go anywhere else. Polar Ambassador. Let's see if that comes up. All right, that comes up. Wow, this is not. Let's try here. Polar cloud. Okay. And of course, the timing couldn't be any better. The polar cloud's down. They'll be working on it. I'll see you guys at 9:05. Thank you very much, Mr. Cato. We'll get out of here for the high school class. See you guys at 9:05. We'll start printing everything then.
All right.
All right, take
Good
care,
night, guys.